we're going to need a workforce who actually understand what quantum computers are. And so PhD students who are going through research in these institutions and are reading the papers and learning about these things are going to be the people who can enable that technology in the future. So training that STEM workforce for quantum computers is going to be extremely important.
We are developing new methods to create novel devices that can improve efficiencies and lead to new types of electronic development. Semiconductor is a type of material that is somewhat conducting. There are insulators and conductors. Semiconductors fall in between, and you can control their conductivity by how you prepare them.
And our focus is to grow good quality, high quality to monolayer transition metals like chalcogenide. I have learned to grow two-dimensional material and how to characterize them using photoluminescence and Raman spectroscopy. Photoluminescence, or PL, is photon emission from material that is result of optical excitation of the electrons in the material.
I'm working with 2D material exfoliation, graphene specifically. We're trying to mechanically exfoliate it using the Scotch tape method, and that way we can put it down on substrates of our choosing. We're mostly using silicon dioxide, and then ultimately we want to perform photolithography on that, so we'll be able to test the electrical kind of behavior of monolayer graphene.
Three major things that I've learned from working in Dr. Stinaff's lab are photolithography, using the AFM, and growing 2D materials using CVD, or chemical vapor deposition. So AFM stands for atomic force microscopy, or an atomic force microscope.
Photolithography is based around one of our focuses, which is nanoelectronics and the study of 2D materials. And this has an end goal of technological advancement, both in research. We can further our research with this, and then also it has industry applications with semiconductors. Just 2D materials have a lot of really exotic behaviors, and they're really interesting.
We have been venturing out not only to 2D materials but rare earth doped 2D materials. And this field is quite new. We would be one of the earliest labs to do research on rare earth doped 2D materials.
What we do, though, in our lab is actually start from scratch and grow them by individual layers into how many ever layers we desire. What's important about our technique is that we can grow them on a larger scale and have as grown devices coming out of our furnaces once the process is done.
Having the skill set to solve difficult problems in the lab often translates really well to solving really difficult problems in society. So training the next generation of problem solvers is really, if you like to solve hard problems, I think physics is a fantastic place to be in.